should all have a handout. Right. Can you grab a handout? Wait. There's a handout. Nope. There's a new handout.
One of these?
Yeah, not that one. That's mine. It's over there on the turn around.
Oh, this one's there.
I know, I don't usually leave piles of things. That would have been way faster for me to just... We're all falling apart. We're going to make it. So, one, I hope you guys have a great holiday break. Enjoy some time of relaxation. And when you get bored of that, don't forget you have a couple of things that are upcoming in this class. So, one, mini exam 6 is due December 1, which is next Wednesday. So all the same rules apply. Chemistry and life, whatever it is. Nope, mini exam 6 and chem and life do the same day. If over the next 5 days, so tonight at midnight you have your Alex from last week due, you can do anything you would like for the next, until I think the 27th is Saturday. We're going to go with that. Until Saturday. There is stuff from today's lecture that is due next Monday. They are available during Open Pi, but they will, I don't want to say open because that sounds like they're previously locked. You will have to go look for them in the assignment for this upcoming week. Or you can wait until next Monday, which is what your plan was anyway, and do them then. It will work the usual way it does. You are more than welcome to complete 100%. Can you grab one of those handouts? You can do 100% of the rest of your homework. It is due on your final exam. Well, I'm thinking about it. Some of you have, I don't want to call them adult jobs, but you have jobs where you go to work all day. Your final exam starts at 3 o'clock. If you have a job where you currently get off at 4, if you could send me an email, we can try to set up something to where you could continue to go to work as normal. You don't have to take the day off. If this doesn't apply to you, I'll see you at 3 o'clock on whatever day that is, and we'll go from there. But I'd like to highlight that so that if you either need to ask off or whatever else, you can do that. Any questions, thoughts, issues? Okay. So, today, I have provided a handout which has a table on one side. We're going to work through a lot of this. On the back is a graphic. You will need to memorize everything on this graphic. This feels like I'm just telling you to memorize stuff. We're going to learn it in the first 4 pages, and then this is for reference. So today, we want to build on Lewis dot structures. Lewis dot structures are 90-degree angles. So what we're going to learn is to take our 2-dimensional structures and make a graphic representation, still in 2D, although I did bring models. We want to make them into a 3D structure. So why do we care? And how does this affect your life today? So most of us have taken some type of either an antibiotic or an antidepressant medicine. Anything you get from the pharmacist, pretty much, has a packet of papers in there, and if you open that, it has a chemical structure. Most people don't look at this, but if you open it after today's lecture and definitely next week, you'll be able to look at it and be like, oh, I know what all this means. So why does this matter? If you are in medicine or hope to be in medicine, when we think about these drug molecules and how they interact with proteins, it's a fit environment. So we need to know what is the structure of the molecule and what is the structure of the protein. How do they fit together in order to make this interaction happen? The same argument could be made for engineering complexes, or I would argue that this is the skill from Gen Chem 1 that is the most useful. Followed promptly by dimensional analysis so that you can alter your recipes when you make mac and cheese or whatever it is you're making for Thanksgiving. Those are the skills. This is the one that I think is my hope that you go home with and you're like, oh, I learned that. So, today we're going to talk about 9.1. Those are the 4 sections. If you flipped through, you've seen that there's a 9.5 section. That is just, we'll get there when we get there. but it's not the full book chapter. So the book chapter, I think, has 9 sections. We're only doing 1 through 6. So molecular shapes. If we look at this graphic, so on the far left, we see a Lewis dot structure for carbon tetrachloride, which is, as one might expect, carbon in the center, 4 chlorine atoms, 90 degrees apart. So that structure includes a couple of things. One, all of these chlorine atoms are 90 degrees. 90 degrees apart doesn't actually take, sorry, I didn't catch you just in time. So 90 degrees apart is fantastic in 2 dimensions. But in 3 dimensions, I'm not sure that this is the right angle apart. We want all of these atoms, or lone pairs, to be as far apart as humanly possible. So today we are going to look at my sketchy model system that I bought at Hobby Lobby all by myself. And I will hopefully not hurt myself. Well, that's not in the right place. Give or take. Best of luck. Sorry, I'm trying to hold these to where you can see them and it's not going to work. In this case, we have this model. We have these smaller spheres are the chlorine atoms. This larger sphere is the carbon. Technically, those are out of proportion, but the central atom is what we think about in terms of shape. These pieces out here are more like accessories. We want to be able to draw this in 2 dimensions. I'm not going to lie, I'm a horrible artist. However, I'm going to show you what I expect. So, we put our carbon in the center, and we want to annotate that our molecule looks like this. We have one up here and one out here. These 2 are in the same plane. The plane means they're in a line. So I'm going to flip it. In theory, if we set this up just right, both of these, and no one on the internet can see us, these 2 are in a line. That being said, these 2 down here are also in a line. It's kind of the deal with this structure. But in a tetrahedral molecule, these 2 are in the plane of the board. We have one that comes out in front and one that's behind. And we can add our chlorine molecules all around. In this case, these are called, I don't want to say lines. We have lines that are in the plane. So this is in the plane. This back here is out of the board. And these are behind. So what this really looks like would be this. So I'm going to use my arm as the plane because maybe not obviously, I cannot in fact project something behind. But that doesn't really work. This one is clearly in front and this one is clearly behind. We've lost our aspect ratio. But it looks kind of like this. So what we want to do is take a Lewis dot structure and figure out how to draw these. So today, we are going to look at lots of different structures. And at the end of class, we're going to apply all the information. We're going to try to move as fast as possible because a lot of this it feels like it doesn't make sense until we start using it. It's a lot of disparate information. There are a lot of patterns, which are good because more often than not, it feels like Jenkin 1 is a bunch of discrete data points that never fit together. It's not how this works. So we are going to look at the Vesper model or the valence shell electron repulsion model. It's going to give us a 3D shape. And we are going to think about what it looks like with lone pairs and without lone pairs, or bonding electrons and non-bonding electrons. So, a couple of, I always like to start with the definition so that as we talk about it, you're not like, I don't know what that word means. So the electron domain geometry is the number of things connected to the central atom. All of what we're going to talk about today is in reference to this central atom. So if you look at this structure, there are 4 things connected to it. It doesn't matter if it's atoms or lone pairs, it's just how many things are physically connected to the central atom. So steric number, or Sn, is basically the same thing as the electron domain geometry. The steric number tells you what the electron domain geometry is, and you'll find that the electron domain geometries are more of like a broad network. Everything with 4 things connected has the same electron domain geometry. But the molecular shape is only for the things that we can see. To date, the majority of spectroscopy, structural spectroscopy equipment doesn't actually show electrons. We just see where they could be. So what we're going to see is that the bond angles, if this converts to a lone pair, are going to just, I'm afraid these are going to break. They're just going to get a little bit smaller. And so what we're going to look at is how does that affect what they look like in 3D shape. The words that we want to think about, the things that we're going to think about are the bonded pairs, so the electrons involved in bonding versus a non-bonding and or electron pair, because that's how we're going to determine the structures. When you look at this graphic, so this is the front page that has, starting on the left column, steric number. If you flip through this, you can see that there are steric numbers 1 through 6. We're going to start with 6 and go down to the less complex. I'm going to basically fill this out as we go across. However, as you go all the way almost to the end, there's a column that says hybridization. We're going to leave that alone until next week. But it is relevant for most of these structures, so we can't ignore it. Please bring this back next week. I say that about all my handouts. I kind of mean it about this one. So, let's think about this. If we have one, two, three, four. If I have 6 of these, and one already connected because it won't come out. If we want them to be as far as humanly possible apart, we need an arrangement that allows them to be equivalently apart. Now, in some years, or you can do this at home, because you might have marshmallows for some sort of sweet potato pie, and hopefully a gumdrop because you're excited about the holidays. I don't know. You basically need something that you can stick together using different toothpicks. I've done it with grapes. Grapes kind of leak everywhere. It's a bad idea. Raisins don't work. Neither do Cheerios. Just as an aside, you can use anything you want. You can give it a go. But the reality is we want them to be as far apart as possible. If we only have 2 things, 180 degrees is as far apart as we can get. 6 things is a lot of things. But it turns out, if you've ever seen a jack, like the game that no one really knows how to play, but you can also buy them for decoration at many snooty decorating stores, because that's where I picked them up. But the reality is, it's basically 6 prongs stuck around the center all the way around. And it doesn't matter the orientation. So that's what we're going to draw. Now I'm going to endeavor not to stab myself. Please ignore the fact that these are all kind of wobbly and a little off-centered. I obviously made this myself when I went to Abu Dhabi. So I have math skills. These are not them. The question is, how do we take this thing that looks the same no matter how we rotate it, slightly different, you can make arguments like, okay, this is different than that. But no matter how we rotate it in these planes, they are the same. So the question is, how do we draw this? How do I set this down? Over here. There's a handout down in the front if you would like one. So we're going to start with the steric number of 6, which is arguably the most complicated because it has the most things stuck around the central atom. But I think it is easier to take something apart than to try to build it up. So for our steric number of 6, we're going to start with a base AX6, which is 6 atoms, 0 lone pairs. So when we draw this, we have our central atom A, and something that looks like this. This is this arrangement. We have these 2 that are in the plane of the board, 2 out in front, 2 behind. And so all 4 of these are equivalent, all 6 of these are equivalent, and they all look like this. And all of the angles, no matter which ones you measure, are 90 degrees. The electron domain geometry is octahedral. And the molecular shape is octahedral. This is because both the number of atoms and the number of things connected to the central atom are the same. Now, that statement feels like I don't understand what you're saying. Mostly because we've only looked at things where they're all connected. So let's think about what would happen if we go to AX5E, where we have 5 atoms and 1 lone pair. If we have this structure, and I need to remove one of these and convert it into a lone pair, it doesn't matter which one I choose. Hopefully you're thinking like that feels like a trap. It should. They're all the same. It doesn't matter which one you pick. You can pick any one you like. So the orientation shown on the back graphic is this. We have a single one above. So there's the axial plane, which is like the axis, and the equatorial plane, which is the one around the middle. You could draw it like this, but no one does. But you could, and it would still be right. Because you can make it whatever geometry you like, as long as you follow the rules. In this case, we have 1 lone pair down here, and it is going to squish everybody just a little. So when we draw this, we're going to have the same base geometry that looks like this. Everything with this steric number of 6 starts with this geometry. So from here, we're going to put our 5 atoms in this arrangement, and our lone pair goes down here. So the base shape, or the electron domain geometry, is octahedral. The molecular shape, which is what it looks like because we can't see electrons, looks like a square pyramid. And these bond angles are all the same, and they're all slightly less than 90 degrees. There are technical values. I'm asking you to memorize the values that are on the back graphic, which are all just less than or much, much less than. What questions do we have in this moment? Yeah.
So the octahedral and the square pyramid, that goes, so the first one is for the electron domain geometry?
Yes.
And then the other one is for the molecular shape?
Mm-hmm.
Okay. And then they both have, well, there'll be 1 lone pair.
There's 5 bonded atoms in 1 lone pair. Yeah. This, as we fill out more of these rows, you'll be like, yup, I'm all over it.
Why is it that the lone pair pushes everything else just a little bit?
So the lone pair pushes everything else a little bit due to the electron-electron repulsion in a lone pair. So it basically just kind of expands, gives little elbow room. And when it does that, in order to give the pair of electrons enough space, they push everything, and it's small amounts.
Right.
In most cases. That's all it is. Other questions? So, yes.
Just kind of expand on what you said, so again, them pushing for like lone pairs causing extra push is the reason why even though we have the same number of not lone pairs. What's the opposite of like the x's?
Like an atom.
Yeah, sorry, atom. Good. That reasoning is why, even though we have the same number of atoms for steric number 3 and 1 lone pair, and steric number 4 for.
So I'm going to actually ask you to hold your questions about steric numbers not 6 until we get to those numbers.
Okay.
Because you may have seen these before, but other people might be like, I've never seen this before. So as we continue, we have the same graphic. These are now not all the same. So we need to remove another one. These 4 are pretty clearly all the same. Well, maybe not, they're not. I'm telling you, they're all the same. When we look at them this way, they're all the same. This one is different. So we want to remove the one that is different. If you removed this one, or anything in this plane, it would effectively make a non-equivalent structure. So now we have this. This, you could imagine, if you connected the lines, looks like a square. They're all in the same plane, which means they're relatively flat. Mine are not flat because I'm human. In this case, this is a steric number of 6, meaning there are still 6 things connected. So we have AX4, E2, which is 4 atoms, 2 lone pairs. And so when we draw that, we get something that looks like this, where it is a base octahedral followed by square planar. Questions? Oh, bond angles, 90 degrees. These are back to exactly 90 because the top lone pair pushes against the bottom lone pair and flattens everybody out. So now we need to remove a third atom. Do any of these have any different structures? No, they all look the same. So now we have this molecule. It kind of looks like a T. Thus, they have named it T-shaped. So the way we can draw that for the AX3E3 with 3 atoms, 3 lone pairs, it looks like this. So we have 2 X's on the top and the bottom. These 4 are relatively equivalent. We have 1 X and 3 lone pairs. And it looks like this, and so it is octahedral followed by T-shaped. And this bond angle is slightly less than 90 degrees, which means that it's a little bit like this. It just kind of squashes them just ever so slightly. Questions? So now we have AX2E4, which is 2 atoms, 4 lone pairs. If we have this structure, it really only makes sense to remove this one, because if we removed this, these 2 would be too tight. This structure, we will see frequently, is linear, because it makes a line. Sometimes we're clever, sometimes we're just regular. So we end up with our atoms on top and bottom, and our lone pairs around the middle. And this angle is 180 degrees, and it is octahedral linear. Questions thus far? if we have 5 things connected to our central atom, we need them to be far apart. It's going to look somewhat similar to how they were connected with octahedral, but we don't have as many. So we're going to expand around the equatorial plane. Where we have 5 things, roughly, these 2 are 180 degrees apart. These 3 should be, although I don't think they are, because I didn't use a protractor, roughly 120 degrees, which is 1/3 of a circle. So what you can see is, unlike octahedral, where they were all the same in the beginning, these are not. We have 2 that are going to be across from each other, and 3 in a plane. This is our Trigonal Bipyramidal, which is 2 pyramids with basically triangle bottoms stuck together. So let's draw. The other arrangement that people use is this structure, where you took this molecule and you laid it down. And it would help if it didn't rotate. It kind of looks like it could rock back and forth. People use these, they often set them on their desks as some sort of nifty tripod structure. So for a steric number of 5, it starts with an AX5, with an A in the center, and our 2 X's on this way. Previously, by and large, we had 1 bond angle. In this case, we see a 90-degree angle here and a 120-degree here. So the equatorial are 90 degrees to the center. No, the axial are 90 degrees to the center. The center ones are 120 degrees apart. This one is 90 degrees to these. This one is 120 degrees. Oh my gosh, I'm gonna die. These create a line, and these are 120 degrees apart. So these are Trigonal Bipyramid and Trigonal Bipyramid. So now we're going to do the same thing. We're going to walk from 5 atoms to 4 to 3 to 2. So AX4E is 4 atoms, 1 electron. We want the atoms to be as far apart as possible. In order to do that, if we take this one away, they're all really close. So we want to remove one from the equatorial plane. And you get this structure, where you have 2 in a line and 2 over on the sides. The graphical or the molecular shape is actually called seesaw. Now, you could, I don't want to say you could imagine, this kind of looks like a seesaw or a teeter-totter. I don't know what you grew up with. We called them teeter-totters. I will accept seesaw, sawhorse, or teeter-totter because it amuses me. Alex would prefer that you call it seesaw or sawhorse. So in this case, we have A, X, and this is Trigonal Pyramidal. Nope, Trigonal Bipyramid. And this is seesaw. And so these bond angles are less than 90 and less than 120. Because that lone pair pushes everything back. Minuscule amounts.
Sorry, are we measuring what are we measuring there?
So this, let me find. So the less than 90 is this angle. Well, that didn't help at all. This, that looks, we can't draw this on the internet. I'm so sorry. These are my nightmares. They're coming true. Let's just try again. We're looking at the angle between x1 and x2, and that, this is way better than circling things, is less than 90. The angle between x2 and x3 is slightly less than 120. So it's the same thing here. So this is the x1 and x2, and this is x3 to x4. I drew something here, I thought. Those are the bond angles we're looking at. Any questions? Yeah.
So then, our X1 and X4 on AX4E, are they still 180 degrees from one another, or are they also pushed slightly away from each other?
They're just slightly away.
Okay.
So it would be slightly less than 90 on whether it was this one or this one.
So then, X1 and X4 to the electrons is just slightly greater than 90.
This to this,
Yes.
we can't measure that angle. So you can only measure angles between what you can see.
And the important distinction is what we see directly on the diagram. We don't need to memorize the exact angles between the topmost and the bottommost X and AX, right?
No, you're going to need to memorize this.
Yeah.
I don't understand what you're asking.
Like the angle that he asked about earlier, that he said was slightly less than 180. We don't need to worry about that one, right?
So you should be able to label any bond angle on this structure between atoms. He also asked about between X1 and the lone pair, but we cannot see this, so we can't measure it. But this X to X would be slightly less than 180.
After we know that.
So now we have AX3E2. I lost my structure. We have this. So we have two that are axial and two on the equatorial. We need to remove one. We want our elements to stay as far apart as possible. You could remove this structure. What structure is this? T-shaped. Which should look very familiar. And these bond angles are slightly less than 90 degrees, whether you would look at this bond angle or this bond angle. There is an alternate arrangement where you could also remove your two electrons and put them in the axial positions to where you would get this, which the shape here is trigonal planar. And they are 120 degrees. Both of which are acceptable. They are both equally correct. There are some reasons why one is preferred over the other. If you have three of the same things, it prefers this. If you have three of different things, or how big they are, it could be this. I will accept both at all given times. And last, I don't want to say but not least, we have AX2E3, which is going to look like this, but with one less lone pair. Because when we remove this one, the last one will come out of this structure, and now we have, again, a linear molecule. below, those are not sets. To where we have trigonal, bipyramid, linear. Question about steric numbers of 5 or 6. Yeah.
So that one was 180.
Yes. Good question. Other questions?
The measurement is for the molecular shape, right?
Yes.
Okay. So anytime that you would have like the molecular name, it would be corresponding with, like it's the same for every atom, or like for every structure. So like linear algebra would always be 180,
Yes.
and then T-shape,
They'll always be slightly less than 90. Mhm. So you can see in both steric numbers of 5 and 6, which are structures that violate octet, because that's how you get 5 or 6 things connected. You can imagine that we're going to see these in some structures, but not all. So these are our octet rule breakers. Let's now talk about things that, I won't say conform to octet, but that live in the octet land. So now we are going to look at steric numbers of 4. Is it okay if I erase these? Are we all? So for a steric number of 4, our loose dot structures put them 90 degrees apart. We looked at the carbon tetrachloride earlier that was pretty clear that it wasn't 90 degrees apart. So they are what turns out to be 109.5, which many of us can't draw that. It is more than 90, but less than 90 plus half. Are not right. Better. These are not exactly correct, but we can all, let's use our imagination. So this angle is 109, as is this angle, as is any angle you look at. The thing is, you could rotate this in, I don't want to say 100 different ways, but you could. What's important is that we have 2 in the plane of the paper, 1 in front and 1 below. They can be in this arrangement, or this arrangement, or this arrangement, or this arrangement. There's a lot of choices. You may put them anywhere you like. So in this case, for steric numbers of 4, we have 4 atoms, 0 lone pairs, and it is AX4. And this angle is 109. Technically 0.5, but the sheet only has it as 109. You're only required to know 109. It is tetrahedral. Tetrahedral? So in this case, all of these are the same. This is what we see when something satisfies octet. We're going to draw this a lot. So from here, we need to remove 1. Because they're all the same, it doesn't matter which one you remove. I'll remove this one because it worked. We can hopefully see that we're going to have a lone pair up here and 3 equivalent bonds, that because the lone pair squashes them, it's going to go like this. Structurally, you could imagine that this looks like a trigonal, like a pyramid with a triangle base. So they call it Trigonal Pyramidal. So in AX3E, We have an A, where we have 3 of our atoms in one lone pair. This is less than 109. And it is tetrahedral trigonal pyramid. I don't particularly care if you call it trigonal pyramid or trigonal pyramidal. Those are really the same in my life. Either of those is acceptable. From here, we need to remove another one. You may pick any of these. They are technically all the same. To create our AX2E2, we have this structure. We have 2 atoms, 2 lone pairs, where we have our 2 atoms in the plane of the board and our lone pairs coming in and out. We often see this drawn also like this. Where it looks like this with our lone pairs up and back. Either one is fine. And this is tetrahedral bent. And this bond angle, or this one, is much, much less than 109. So it technically goes 109, 107, 105. I will accept that annotation. Or less than and much, much less than if I ask for the bond angle. Let me rephrase. When I ask for the bond angles, I will accept either of these annotations. Questions? I think in the chart it talks about AXE3. Is that on there? That's this with 3 lone pairs. So really it's just a line. So if you wanted to draw that for AXE3, which would be something like HCl, what you would have is AX followed by 3 lone pairs. And this is considered tetrahedral linear. And there is no bond angle because 2 points make a line. No matter how you look at it, they are either 0 or 180 degrees apart or 360. This connection needs another piece in order to measure the bond angle. Questions about steric number of 4. So let's look at steric number of 3. If we have 3 things and we need them to be as far apart as possible, we can think about the Trigonal Bipyramidal, which had 5, 1 on the top, 1 on the bottom, and 3 around the equatorial plane. It feels like with 3 items, there should be some way to make some cool 3D structure. It turns out that what we get is something where they're basically, these are not roughly 120, but you could imagine that they are. We get 120 degrees apiece from all different types of angles. And so this is trigonal planar. So for a steric number of 3, where we have AX3, we have where these are 120, and that is trigonal planar, trigonal planar. From here, we do the same thing we've done with all the other steric numbers. We're going to, that works. We're going to lose 1. It converts into a lone pair, and so now we have this structure. It should look somewhat similar to the bent structure that we saw for a steric number of 4. So for AX2E, we have a lone pair, and these are less than 120. It is trigonal planar bent. I am going to opt not to draw the AXE2 because it is this structure with two lone pairs and a single bond. It is also linear. It's also not something that we typically observe. It's a very weird electronic state that basically doesn't exist in Gen Chem 1. Questions about steric numbers of 4 or 3? We have one steric number left, I think. 2. Steric number of 2 and 1. When two things are connected to the central atom, how far apart should they be in order to be as far apart as possible? 180 degrees. We have seen this structure before for the AX2E4 or E3 in octahedral and trigonal bipyramidal, respectively. So in this case, for a steric number of 2, what we have is this, and this bond, as per always, is 180, so it is linear. Linear.
Is this for AX2 or AX3?
Say which one?
Is it for AX2 or AX2?
It's the AX2, so the first line. You could also do AXE, but it will look like this. Or AXE with A, lone pair, X. It is also linear, but again, we don't typically see this structure because it doesn't have octet. It only has, the central atom only has, in this drawing, 4 electrons around it. So it would be somewhat rare in that case. For the AX, the steric number of 1, this is almost rarely occurred. It's just AX in any arrangement. The bond angle is non-existent. This is what you would see for H2. 2 atoms connected to each other. That's it. So what questions do we have about these types of drawings before we move to the practical use of this, which is, in my opinion, more exciting? You are responsible for all of the information on the back page. So what I will ask you to do is to draw a structure and then provide the bond angles, the domain geometry, and the molecular shape. There are on the page, the 3rd page, there are 8 examples. I'm going to post a worksheet, and you probably before Monday need to draw somewhere around 40. If after 15 you're like, I have no issues, you may stop. If after 15 you're still like, I don't know, I recommend that you get closer to 40. I'm going to give you somewhere on the order of 30 examples. The more of them you draw, the easier it is. So what do we do with all this info? So you should have a copy of a guideline sheet that started with Lewis dot structures and ends with how to use a Vesper structure. So to draw a molecular structure, you will have drawn a Lewis dot structure. So any of the Lewis dot structures you drew last week, you can now draw a Vesper structure. From there, you're going to count the number of domains, things, stuck around your central atom. You're going to determine the electron geometry, so the base geometry. There are 5 choices. You can have 2 things, 3 things, 4 things, 5 things, or 6 things connected to your central atom. It's only the central atom. Just count whatever atom is in reference to, whether it is one atom in a huge molecule or some sort of small atom or the central atom, usually the underlying. Using the number of atoms, you're going to determine the molecular geometry or the molecular shape, which feels like there are a lot of different things that I just told you. So practically, one, I'm going to erase the board, and then we'll look at an example. While I erase, you can start by drawing the Lewis dot structures, because at this point you should know, okay, I can come up with a Lewis dot structure. We're just going to take our Lewis dot structures and go what feels like a big step, but it's just a smaller step forward. So your Lewis dot structure for XeF2 should have xenon in the center with two fluorines connected to it, both of which have octet, followed by 3 lone pairs around the central atom, give or take. So, drawing this Lewis dot structure, and yours may have the fluorines in a different arrangement or something else. There's a lot of choices here. But the question will say, draw the Lewis dot structure, draw the Vesper structure, name both the electron domain geometry and the molecular shape. So from here, we need to draw our Vesper structure. How many things, atoms or lone pairs, are connected to the xenon? 5. What is the base shape of anything with 5 elements, or 5 things? Trigonal Bipyramidal. So now we're going to draw our xenon in the middle, and we know it's going to look like this. The thing is, we have 3 lone pairs and 2 atoms. So we want to make sure that our atoms fall in line with the repulsion of lone pairs. So we're going to put our fluorines on the top. We are going to add their lone pairs, as well as the lone pairs here. And then in this case, it would be Trigonal Bipyramidal linear. What questions do we have about this example?
I have a question about the Lewis dot, let's go back to that. When do we know not to do like the double bonds and all that stuff?
So in this case, there's 2 things. One, fluorine never has double bonds. It's, I don't want to say incapable, but it just can't. So there's that, and you would have determined that using the formal charge. So in this case, the formal charge on xenon is 8 minus half of 4 minus 6, which is 0. So in that case, you wouldn't need any double bonds. We will get to double bonds. Most of the examples today will have very few double bonds. Yeah?
So how does everybody know that it was 5?
It's a good question. So there are 2 atoms, and then there, depending on how you drew yours, mine kind of looks a little bit messy, but there's 1, 2, 3 lone pairs on the central atom, right? So together that gives you 5. It's okay that this feels a little like, I just have so many questions about what's happening in life. I think the best thing to do is to give it a go. If you get stuck, I'll help you. So for the remaining 3, go ahead and do that. The underlined atom is the central atom. It is the atom you care about. If you finish these, my little speedy people, I'm going to give you a few other examples so that you may take them home with you to work on, I don't want to say at a later date, but if you would like. We have X, E, F, 4.
was a question that I just kind of, took the class. I was gonna ask if, like, a different bond between, like, a metal, like a permanent bond and a fluorine bond, right? Have different, amounts of push. Yeah. Propulsion on the rest of the structure, but that's not.
Actually, in the next section, which we will not get to today, it talks about polarity, and so the arrangement of non-equivalent atoms can affect how and what it does in 3D space.
Cool. Also, your right hand.
Oh, yeah. It's because I don't want to pick on my eraser, so I just do this. How's it come? It's just getting a little. Oh, right. When I was doing what I was thinking. There are, if you take organic, there are slight genetic preferences, but then come on, I don't care. If you follow these conventions, or you just stick them on the right arrangement, I'm happy. So as we look at ammonia, sulfur hexafluoride, and dichloromethane, as we look at these structures, if we look at NH3, your Lewis dot structure likely looked like this. So how many unique things are connected? 4, which means it's base tetrahedral. As soon as it's steric number of 4, you can draw the same structure. Nitrogen in the middle. It turns out that these could be rotated in any way. You may put your hydrogens or your lone pairs anywhere you want. I almost always put mine at the top, just because that's where I like it. You can put yours somewhere else. It is not wrong. We have our lone pair here. So this is tetrahedral, trigonal, pyramidal, so for SF6, how many things are stuck to the central atom in your Lewis dot structure? 6. So our Vesper structure is base octahedral. It in fact has no lone pairs connected to it, so we can just stick our fluorines everywhere we have them, and then include all of our lone pairs. Which, yes, will take you a while, but they are important. So in lab, these are octahedral. If I ask for both and they're the same, you either need to write the same word twice or indicate that they are both the same. You could put electron domain and molecular shape, octahedral, or you can write it twice. Either one works. If you only write one, and you don't annotate anything else, you will not get credit for the other one. In lab, it is possible that people told you you do not need lone pairs on a Vesper structure. There are different conventions on that, and I personally find it very difficult to explain why this lone pair lives and none of these do. So we're going to draw them all. It just makes it so much easier to just bring them all with you. I know, it's not fun. But some atoms, we care about them, others we don't. I think it matters. It will matter when we get to the more complex structures. For carbon CHCl2, we would get this structure. Which is tetrahedral. And these are 109.5. It doesn't matter where the chlorines go in this molecule. There are some preferential arrangements, but for the purposes of Gen Chem 1, I think that that's slightly outside the scope of this class. In this case, that is probably, I think the preference is that they're all the same also. So whether it's here or here or here or there, they're all the same. So it will change. So next week, we'll start to talk about polarity. And molecular polarity can be affected by the substituents. What questions do we have before we, this is as far as I plan to go today. Any questions? I would recommend that you practice. I'd recommend that you work on it. I do have your mini exams